Welcome to the Chem 1A pre-lab lecture for Experiment 7, Determining the Empirical Formula of a Compound. Our learning objectives from this experiment will be to practice quick and accurate mass measurement, to understand the concept of the mole, and to learn the relevance and the use of chemical formula. The experimental objective will be to determine the ratio between magnesium atoms and oxygen atoms when magnesium is combined with oxygen to form magnesium oxide. This ratio is called the molecular formula. So in order to talk about how many atoms combine with how many other types of atoms, we need to be speaking in a quantitative manner that actually looks at atoms as individuals. But because atoms are so tiny, we can't really talk about them as individuals. Their masses are too small for us to weigh, we can't see them, and instead we talk about the amount of atoms in a group. So just like you might tell me how many pairs of socks are in your sock drawer, or measure the number of donuts or eggs or muffins by the dozen, we talk about atoms in terms of the mole. And so you all know that a pair of socks includes 2 individual socks, and that a dozen eggs is 12 eggs. Well, a mole of atoms is simply 6.022 times 10 to the 23 atoms. Now this may not seem such a simple number, but practice it a few times and you'll have it down, and it really is no different than dealing with the 2 socks or the 12 eggs. If I had 24 socks and I wanted to know how many pairs of socks I had, what would I do? I would simply divide 24 by 2 to say that I had 12 pairs. Similarly, no matter how many atoms you have, you can divide that number of atoms by 6.022 times 10 to the 23, and that will tell you how many moles of that substance you have. So where did this number come from, this mole number? Well, you'll see in my previous slide that I called the number that equates moles and atoms as A sub n, right here. And so that indicates Avogadro's number. Avogadro was an early scientist who studied mathematics as well as chemistry, and he defined the number of carbon atoms that it would take to build up a mass of 12 grams as being a mole of carbon atoms. This may seem arbitrary to you at the moment, but once we get to chapter 7 and we're talking about the structure of an atom being composed of protons, neutrons, and electrons, it will begin to make sense. And you will understand the pattern that we see below here, where the molecular weight, or the mass of a mole of an atom, is roughly twice its atomic number. So on the left with lithium has an atomic number of 3 and a molecular weight of 6-ish. Carbon was our gold standard here, so with its atomic number of 6, it would have a molecular weight of about 12. Similarly, oxygen, atomic number of 8 and molecular weight of 16. Aluminum, 13, atomic weight or molecular weight is 26. From these examples, I hope you've come to realize that even though Avogadro's number, the definition of the mole, is such a large number, 6.022 times 10 to the 23, having a mole of a given type of atom isn't really that much matter. It's only a few grams, and this is a very nice number that's easy to weigh in the chemistry lab to compare different types of substances and determine yields and percentage compositions and molecular formula, as we will be doing today. Another thing I hope you've noticed is that as we increase in atomic number, we're increasing in molecular weight. So that means if we look at a periodic table, as we go from hydrogen to helium, lithium, beryllium, all the way down until we get into the heavy metals such as platinum, gold, and mercury, we're getting larger and larger atoms And so the amount that a given type of atom weighs is going to be dependent on its atomic number. And so if I have 12 grams of carbon and 12 grams of oxygen, I do not have equal amounts of those elements. In fact, I would have about 1 mole of carbon and slightly less than a mole of oxygen, because 12 grams divided by the molecular weight of oxygen being 16 would be about 3/4. So it would be about 0.75 of a mole. And that's why we need to know about the mole and molecular weights in order to determine molecular formula in a chemistry lab. Okay, so what again is a molecular formula? A molecular formula describes the ratio of independent atoms within a compound. So you're all familiar with the chemical formula or the molecular formula of water, H2O. And so what this is specifically saying is that in every water molecule, there are 2 atoms of hydrogen that have combined with 1 atom of oxygen. Similarly, carbon dioxide is written as CO2. So the subscript indicates how many oxygen atoms combine with how many carbon atoms. If we do not have a subscript, we simply assume there is 1. So in carbon dioxide, CO2 indicates 1 atom of carbon combining with 2 atoms of oxygen. You might also know that your regular table salt that you season your meals with is sodium chloride. And in sodium chloride, we have 1 atom of sodium combining with 1 atom of chlorine. And so it is written simply as Na for sodium and Cl for chlorine. Because different atoms have different atomic weights or molecular weights, we cannot determine the ratio of atoms in a compound simply by weighing the amounts of each type of atom. In my example of water here, you can see how if we have 2 hydrogens for every oxygen, that's the same as saying we could have 2 moles of hydrogen for every 1 mole of oxygen. So if I look at my mass below, 2 moles of hydrogen would weigh 2 grams roughly. 1 mole of oxygen would weigh roughly 16 grams. So if I look at my molar ratio, we see that we have 2 hydrogens for every 1 oxygen, just like the molecular formula of water says. However, if we simply looked at the weights of these 2 types of atoms, it would appear that I would have 1 hydrogen for every 8 oxygens. So you can see that the mass is not correlated with the ratio of atoms in a compound. Instead, we can use the molecular weights, which are given in the periodic table, and use them to determine the molar ratio from mass ratio data that we can collect in the lab. To determine the molecular formula of magnesium oxide, you will begin by obtaining a clean crucible and weighing it to determine its empty weight. You will then put a clean piece of magnesium inside that crucible and weigh it again to determine the mass of the clean magnesium inside the crucible. In step 2, you will heat the crucible with your Bunsen burner and allow the magnesium to combine with the oxygen in the air through combustion. In this way, your magnesium will actually gain mass as it burns because it is adding the mass of oxygen molecules. Once combustion is complete, you will determine the mass of the magnesium oxide and subtract the mass of the magnesium that you determined in step 1 to find the mass of oxygen that was added. This is the combined oxygen. So from the mass of magnesium from the beginning and the mass of the oxygen from step 3, you can find the mass ratio. And then using the molecular weights from the periodic table, you can determine the molar ratio of magnesium to oxygen. More details about this procedure are in your lab manual. However, this is the overall idea behind the experiment, and I hope it allows you to visualize the purpose of each of the steps in the lab manual. Okay, a few technical tips to help the lab go smoothly. I find that if you bend your magnesium strip so that it's just a gentle curve, and that curve lays directly against the sides of the crucible, then your combustion will go much more quickly. So I highly recommend bending your magnesium strip and letting it lay against the crucible as much as possible at the beginning. It's also very important that the crucible lid be atop the crucible, but a little bit ajar so that the air can get in. Otherwise, there will be not enough oxygen to combine with your magnesium. It's important that the lid is atop the crucible, however, because when the magnesium burns, it emits bright UV light that can damage your eyes. So put the lid on, but leave it a little ajar to let the air in. Also, just as I mentioned, do not stare at the burning magnesium, as it will hurt your eyes. It's very, very bright. Once your combustion is complete, the magnesium should look like ash. It should be flaky white, and there should be no remaining silvery metal. In order to help the combustion go smoothly, first make sure that you've adjusted your Bunsen burner for the hottest possible flame, like we learned in previous labs. If you do not remember how to do this, ask your lab instructor for assistance. Okay, and just to wrap it all up, a few safety reminders. We are using Bunsen burners in this lab, so remember, in addition to bringing your goggles and lab coats to class, make sure you have a hair tie to keep your long hair tied well back so it doesn't fall in front of your face. Also remember that the crucibles will remain hot long after you've turned off your Bunsen burner. So when you're waiting to see if they've cooled, do not touch the crucible directly, but instead use a piece of paper towel to gently grasp the crucible to see if it's cool enough to handle. Also, again, because of the open flames, it's important to keep your benches tidy and free of loose papers such as paper towels and such to avoid the chance of an accidental fire. And also, very important, never leave your lit Bunsen burner unattended. Turn it off before you walk away or leave your lab partner watching it. Okay, good luck and have fun.